In the discussion that, okay, I have to got it. Just give me a second. Okay, so we will continue the discussion that we were having yesterday about asymptotic symmetries. In particular, today we will attack the problem of asymptotic symmetries in the context of electromagnetism. And why this is important, because before going to gravity, I think it's important to have the concepts, tools, and procedure that we will use in the case of gravity. And for that, I think that an excellent laboratory and extremely helpful laboratory is electromagnetism. So we can see if we can develop some techniques in order to attack the more difficult case. So one natural question that arises is, it is possible to find asymptotic conditions or boundary conditions so as electromagnetism is really an invariant or is invariant under infinite dimensional abelian symmetries, besides of as asymptotic symmetries. And this was answered by Andy Strominger almost 10 years ago. And he found that a well-defined scattering problem requires the following antipodal matching conditions, which are relations of the linear Bihar potentials. In this case, can be written in terms of the strength of the gauge potential in terms of the electromagnetic field, and this is a relation that it is satisfied. It is satisfied in this point, which is spatial infinity. And when I say scribe pi plus minus, I refer to the limit u going to minus infinity. And the future of a Pascal infinity, I refer to the limit where v is going to plus infinity. So in this case, we touch this point, this point in the Penrose diagram, and these are the matching conditions that Strominger proposes in the context of the scattering problem. And he found that the asymmetrics of quantum electronic dynamics in that case is invariant under this infinite dimensional symmetry. And he found an infinite amount of conservation laws. And so for, I will not speak too much about this computation, but for details, I think that maybe you know these lectures where all these topics and details are clearly explained. Okay, so due to the existence of these conservation laws is subject to the conditions which are satisfied at spatial infinity, this should be a very important region of the space-time. And one can ask if it is possible to study the asymptotic structure of electromagnetism at spatial infinity. And if we can do this, we will have access to Hamiltonian tools, which are naturally adapted, or we can use or are naturally adapted to an ADM foliation of the space-time or the fields. So using Hamiltonian tools, we can compute canonical generators associated to these searched for infinite dimensional symmetries. So in today's lecture, we'll see how we can formulate consistent asymptotic conditions for the gauge potential, which are leading to an infinite dimensional set of abelian symmetries, together with the corresponding canonical generators. And a key ingredient for this proposal, for this analysis, is the choice of parity conditions for the fields, for the leading order, for the leading behavior of the fields that we have to require in order to have a finite symplectic structure. And I mean with this that we should have a finite action, which is very something that we would like to have, and also finite and integral charges. In this region of the space-time, we will have problem with the news because radiation is not arriving to spatial infinity, so we should arrive to integral charges. Otherwise, we're in problems, and we have to analyze better or finding better asymptotic conditions. So we know that the evolution of genetic initial data on a Cauchy hypersurface develop a logarithmic behavior of the gauge potential at null infinity in the radial coordinate and in the retarded time coordinate. And this is usually not taken into account in the analysis of null infinity. But something that is very remarkable, I think, is that parity conditions the parity conditions that one can find in the analysis at spatial infinity get rid of the logarithmic branch at null infinity. And these parity conditions imply the Strominger matching conditions that I show you in the first slide. It's something that it was shown in the literature. So also in this lecture I will show you the relaxation of the fall-off, so as we can accommodate again a log behavior, but at the spatial infinity in the radial coordinate. It's not the same log that I was speaking about here, but it's another log, another class of logs, and I will show you how to do it consistently. And by doing that, we will find a brand new infinite dimensional set of log U1 charges, which are canonically conjugate. This means that the Poisson bracket between U1 charges and these log U1 charges is a central charge. And these are conjugate to the infinite conserved quantities anticipated by Strominger and collaborators. Also, we'll find that due to the presence of these log U1 symmetries, we can construct gauge-invariant Poincaré generators, which is in the same spirit as the Coleman-Mandula theorem, that we cannot change conserved quantities of the space-time by doing gauge transformations. Something that is not true, for instance, with supersymmetry, which avoids the hypothesis of the Coleman-Mandula theorem. But in this case, we don't have supersymmetry; we have just bosons. And
sorry.
Yes.
There is a question of Eloy. Eloy,
yes, please.
Oscar, it is very nice that there is constantly new results on this topic, but what is the end of this? Did this give me a sense that we don't really understand everything here, and what is your opinion on that? Because we have first this result of Regge and Tate-Boeing forbidding the BMF's behavior in the spatial infinity that was generalized later by Henneaux and his group, and now you have also this kind of logarithmic behavior that was also forbidden. So it is possible to generalize this even more.
Yes, this is something that I will mention at the end of the talk, because we were able to generalize this a bit more, but at least by performing the procedure that I will explain now, I think this stops there. Maybe if you follow some other renormalization procedure in the action, maybe you can generalize this, but I think this is something that is not very well understood by doing renormalization procedures. At least we want to face the problem by just using boundary conditions and not putting divergent terms to cancel the divergent terms in the action. Yes, but at least following this procedure, it stops.
Sorry.
Yes, it stops at certain level.
Yeah, from the Hamiltonian point of view.
From the Hamiltonian point of view, yes.
So you think that we can reach a understanding of this subject, a clear understanding we have anything else from at least from the Hamiltonian point of view?
Yes, because we are in spatial infinity, so we can apply rules. I mean, we have an action which is invariant, and we can compute conserved charges because the action is invariant. But in other regions, like null infinity, this is more difficult. We have news. We don't have an action principle, so it's more difficult to define charges. Yes.
Okay. Thanks.
Okay. So, so in the spirit, as I was saying, so we are able to define, because of these log U1s, gauge-invariant Poincaré generators in the same spirit as Coleman-Mandula theorem. So we start with the action principle for electromagnetism.
Sorry to interrupt you again, but Marcelo has a question. Marcelo, please.
Yes.
Sorry, Oscar. Yes, I have a question related to the how or what is the region of scribe plus minus from the point of view of these hyperbolic coordinates that you mentioned yesterday?
This is something that I will explain, because I will compare the chart that I obtained at spatial infinity with the chart at null infinity, and for that I have to use this Ashtekar-Hansen coordinates. So spatial infinity it's going to open. So we will see clearly where spatial infinity touches null infinity.
Okay.
Yes. I will explain something. I mean, using the coordinates and everything.
Thank you. Okay.
So we start with the Lagrangian for electromagnetism, and this is the action that the Hamiltonian action. This is the Hamiltonian action that one can obtain by doing the corresponding Legendre transformation and following the Dirac's method. I recommend at this point these lectures. This is a pocket book, but it's very short, but it's very deep. If you are boring and you are traveling or something in the bus, I really recommend these lectures by Dirac that he gave at the Yeshiva University in New York in this 64, where all the Dirac method is explained when you want to quantize a system with constraints. So he explained very well detailed, the case of electromagnetism. And if you make the computation in electromagnetism, you will find in general this what he called the extended Hamiltonian action. Extended because one principle could not apply this primary constraint that one can find very easily, because f mu nu, it doesn't depend of the time derivative of the time component of the gauge potential. So this is a primary constraint, and one obtains this Gauss constraint by doing the consistency of the primary constraint. But one could work from the beginning in this formalism, and let's see what's happened in this case. So if we take the variation with respect to the Lagrange multipliers, which are psi and lambda, we'll find that this enforces these constraints, which is the Gauss constraint, which is related to the Gauss law precisely, and this constraint, which is a primary constraint. So the boundary term at infinity is something that depends of certain criteria that we have to use. One is including as many solutions as possible. If we're not including some solutions, it's okay, but we have to say it at the beginning. But it's something that it is expected. It would be nice to have an action which is finite, with a finite value, and also we should find boundary conditions in such a way that the canonical generators are defined, which means that are integrable and finite. Note that also apart from these conditions, the fall-off of the constraint is also part of the boundary conditions, and this is something that we will use to define the set of boundary conditions. Okay, so let's start with the easy part, which are the symmetries, so are the transformations of this action that leave the action principle invariant. In this case, we have these infinitesimal gauge transformations and the infinitesimal Poincaré transformations. Okay, I didn't explain this here, but okay, yes, it's here. So this BI and this Bij represents the homogeneous Lorentz group. These are the Lorentz boosts, and these are the spatial rotations, and also have this A0, which are the spacetime translations, and we can verify that all these transformational law of the fields are closing in this algebra, which is the Poincaré algebra at the end of the day. And one can find the Poincaré algebra. What is a canonical symmetry? Is a symmetry that preserves the symplectic two form. That in the case of the extended Hamiltonian formulation of electromagnetism is given by this expression. This dv is taken in the phase space. It's an exterior derivative taken in phase space. So we don't have to think this as an exterior derivative in the coordinates. That's why I put we use this description. And the invariance of the symplectic form means taking the leader derivative of the symplectic form, and this should be 0. So we use the formula for the derivative in terms of the exterior derivative and the contraction, and we know that as this is a closed form, the dv acting on omega is 0, because you are going to have a t square everywhere. So we will have only this term here. But because of the Poincaré lemma, we have that the contraction of omega must be an exterior derivative. And according to classical mechanics, this is something of classical mechanics, this is the generator of the symmetries. One can show that if you take the boson bracket that you can read from the inverse of the symplectic form with respect to G, you are going to generate the symmetries that I show you. And which are the asymptotic symmetries? So we will change a bit the definition that I gave you yesterday, because we don't have a radiation now. So we can say that an asymptotic symmetry must preserve the asymptotic form of the fields and also being canonical. And being canonical is preserving the symplectic form. So the canonical generator in general will have this form, where we have a bulk term, which is going to be proportional to the constraints of the theory, and also a boundary term, which is a surface integral. This is something explained first by Ray and Teitel in 1974 in the gravitational context, but we can extend this to electromagnetism easily. So we have to define also what is a trivial asymptotic symmetry, which we call proper, and these are those that decay fast enough in such a way that the boundary term is 0, so that on shell the generator, on shell, when I say on shell, I mean on the constraint surface. On shell this is 0, so they form an ideal. And also we have to define large gauge transformation, or also improper gauge transformations, which are transformations with a surface integral different from 0. And these are the ones that can change the physical state of the system at the end of the day. And these definitions introduced by Venguria, Cordell, and Teitel in 1977. Okay, so let's see which are the standard boundary conditions. And before doing that, this is something that we have to be clear from the beginning. What's happening if there is some implicit gauge fixing, freezing physical symmetries? Okay, if we are freezing proper gauge symmetry, is okay, because we are not touching the charges. But if this is not the case, it's not okay when we are freezing improper gauge symmetries. So this is something that we have to take to take into consideration in order to choose boundary conditions. So the standard boundary conditions in electromagnetism are given by this fall-off. So we have 1/r fall-off in the gauge potential and 1/r square fall-off in the momentum and the conjugate momentum. These standard boundary conditions in Hamiltonian form were first used by Henneaux, Julia from Cremer, Julia Scherk, and Silva. So I will call it sometimes HJS. And for that we have to use, and they choose these parity conditions for the leading order of the fields. They choose that the leading order of the gauge potential is even, and the leading order in Cartesian coordinates of the conjugate momentum is odd. When I say Ni, this is the vector that is normal to the sphere at infinity. So if we are changing Ni by minus Ni, I'm referring to an antipodal map. So we are going to the opposite direction in the sphere. And in the usual spherical coordinates, this means to do this change.
Oscar?
Yes.
Oscar, sorry, there is a question of Ignacio Reyes. Ignacio, please.
Hey, Oscar, one question.
Yes.
These HJS conditions, what do they mean physically? Is it like having a finite charge or something like
yes,
this?
Exactly. It's a Coulomb charge.
Okay.
Yes, exactly. You can check on the Coulomb charge, but it's including the known solutions. Yes. Okay.
You have a question?
Sorry, Oscar. Just a simple question also.
I can hear you, but super.
Yeah, we cannot hear you well.
Okay. Can you hear me?
Yes.
Yes, there it is.
No, my question is very simple. What you were trying to convey in this slide is that I must now impose some boundary conditions on my field, but I must take care. So I want to impose some, okay, but I must take care of whether my boundary conditions that I impose fix some gauge symmetries, and maybe even if I don't know, my condition is too much, and I'm killing some relevant degrees of freedoms.
Yes.
And you explained to me that I must take care that I can kill proper gauge symmetries, but I must take care not to kill the improper ones, because those fix talk to me about the physical degrees of freedoms of my theory. Did I got that right?
Yes, I think so. Yes.
Okay. Thank you very much.
Okay. So why do we have to choose boundary conditions, parity conditions? And this is something that was explained in the Relativity paper, the original of 74. They were trying to compute the angular momentum, I think, and for that they found some divergent terms. But by imposing these parity conditions, they were able to kill the divergences. But one could go to the action and actually see that there we need to impose parity conditions. And okay, we start from the kinetic term, and we can see if we replace the boundary conditions, we'll find finite terms plus a term which is going as a log at infinity. So we have to impose parity conditions on the leading order in such a way that this integral on the true sphere is 0. And they impose these parity conditions, orientated one, and then Henneaux, Julia, and Silva, they use it in electromagnetism. So the action is finite. And which are the asymptotic symmetries that they obtain? If we want to preserve the fall-off, we obtain these parameters, these Poincaré parameters, and this gauge parameter. And one can see that the fall-off is invariant, really, under an infinite dimensional UN symmetry. The theorem of this function here, and also the odd functions, the odd part of these functions only. This is because we want to preserve this condition, that this is even. But the problem is that when we put this information in the charge, as pi r is something that is even, so we will only able to see the zero mode of the parameter, obtaining the standard electric charge. And this is the electric field, pi r. So, okay, we obtain a finite asymptotic symmetry. So the group is Poincaré times a U1, one charge U1. Okay, so the answer to this question arrives by exploiting, by arriving to the conclusion that the asymptotic analysis is not exploiting all the available symmetries because of an implicit improper gauge fixing. So we are not obtaining the infinite dimensional tower of U1s that Schrödinger obtained. At null infinity, we are not obtaining this tower at spatial infinity. So Henneaux and Troessaert, they realized how to attack this problem from spatial infinity point of view. And for that, we have to impose, they impose this fall-off, okay, which differs from the standard one in a gauge transformation. And this gauge transformation is not anything, but it is something that leads asymptotically to a twisted parity conditions of the fields. And this is because we will choose this function here as an even function. The partial derivative is changing the parity, so this part of the transformation of the parity of the field is going to be odd. That's because it's twisted. We have both parities, and because the conjugate momentum is not transforming under gauge transformation, this is maintained in the same way as HJS. So we choose this field as an even field under the dipole map. Now we can check that under these self-parity conditions, if we replace this in the symplectic form, we'll find the first term, which dies because of the standard boundary conditions, and also we find this term, which is divergent, but we can integrate by parts, okay? And we will find a finite part and a log divergent part. Why this log divergent? Because here we have an R squared dr, and using the parity condition that I show you, this is 1 over R cubed. This is order 1. So we will have, at the end of the day, the same divergence. But we can use now, and this is the importance of choosing or relaxing the boundary conditions by gauge transformation. We can integrate by parts, and we found here the Gauss constraint. So we can ask for a bit more, and we will ask that the leading order of this of the Gauss constraint is 0, or which is equivalent, we will ask for a faster fall-off of the Gauss constraint. Okay. So, okay, the symplectic structure is finite. Good. But we still have to solve another problem. And the problem is the Lorentz boost problem. And this is because if we apply this transformation, which is representing a Lorentz boost, the symplectic form is not going to be invariant. It is going to give us a boundary term, but it's not zero. If we use spherical coordinates, we can rewrite this non-zero term in this way. And the solution proposed in this paper by Marc and Cedric is using from the beginning the extended Hamiltonian formulation, and this is why I show you at the beginning this extended formulation by Dirac. But besides of adding this term, we will deform the symplectic form by a boundary term of this form. If we do that, we will find that the new symplectic form is really invariant under all Poincaré transformations. So you could find that this is a bit artificial, but at the end of the day, when we make the match with null infinity, it will make sense that this extra field, this extra parameter, because if we add the time component of the gauge potential as a field, so we have an extra symmetry. So the presence of this extra symmetry, it will make sense. So now the action, now the symmetries that we have are Poincaré symmetry, but we will have that the even part of epsilon bar and the odd part of mu bar are improper gauge symmetries. So we have two functions with different parities, and we'll show that this is equivalent in null infinity to choose one function of arbitrary parity, or with no requirement, an arbitrary function. And for doing that, and this is the question that Marcelo asked, is that one can show that starting from this chart that one can compute by canonical methods, one can show that one can arrive to the chart at null infinity, but in the past limit when u is tending to minus infinity. So these two expressions agree. So, and for doing that, we have to use the resolution of the spatial infinity and using the Ashtegar-Hansen coordinates, where spatial infinity now is open. And in these coordinates, okay, this is square plus, this is square minus, and all this region here is I0. So if we want to go to past null infinity, we have to put this s equal to -1 and s equal to 1 in order to go to null infinity, to future null infinity. But this is going to touch only the region where u tends to minus infinity, not the complete set of null infinity, just this region. Okay. Okay, so we can pass this charge to the hyperbolic description, and we will see that there we have a parameter lambda, which is arbitrary. And the thing is that epsilon evaluated in s equal to 0 is equal to epsilon bar, and the derivative of with respect to s evaluated in s equal to 0, this is going to be mu bar. One can show that by solving the equation of the parameter in these coordinates in order to have an action, an invariant action principle. So we have the map here between the parameters at spatial infinity in the coordinates, in the usual coordinates, spherical coordinates, and then in the hyperbolic description. The thing is that this bar epsilon that we have here is really lambda, but evaluated at s equal to 1. So this is the connection between the two descriptions. And one can obtain, by rewriting this term in terms of the hyperbolic coordinates and taking the limit s equal to 1, one will obtain this charge. Okay, this is done in, we did it in the spin 2, I mean gravity, and in electromagnetism is working perfectly. So we can go from one charges to the other ones. Okay. Okay, so the asymptotic symmetry algebra in this case. Okay, so one can compute the boundary, the canonical generators associated to the Poincaré symmetry. Here we have bulk terms. These are not zero in this theory because we are in electromagnetism, and there we have bulk terms, even on shell. This is not zero. This is what I want to say. This is different from zero. And also we have canonical generators associated to the gauge symmetries. We have the Wald term and the boundary term that I already showed you. This on shell is 0. So the gauge symmetry is going to be, the canonical generator associated to gauge symmetry is going to be a surface charge. So the charge, the algebra is given by these brackets. We have the Poincaré algebra. We have how the gauge, the canonical generator suited to gauge symmetries is transforming under Poincaré, and also we obtain that the bracket between two gauge symmetries is 0. So they form an ideal, as I told you at the beginning. So as I show you schematically, these two functions with different parities combine in one arbitrary function at null infinity, and we recover the prescription introduced in the context of the scattering problem in QED. Also, something that I will not explain because of the time, but yes, this is in the papers, is that the parity conditions at spatial infinity, they define initial data in such a way that we kill the logarithms that we obtain in the null infinity in the follow-up at null infinity. This is something very, very cool. For doing that, you have to solve the equations in the hyperbolic description, and then applying parity conditions. And this will kill exactly, by asking for these parity conditions, spatial infinity will kill the branches associated to the logs. The branches associated to the logs are they correspond to
Oscar, sorry.
Yes.
There is a question of Marcelo.
Yes.
Sorry, okay. One question. Could you repeat how do you bypass the Coleman-Mandula theorem? Because here you have this mixed bracket between the gauge transformation and
yes, because we are transforming Poincaré charges. We are changing the angular momentum by doing the U1 gauge transformation. I think something that everybody was calm and was okay with that, but it was a problem. But we are not bypassing the Coleman-Mandula theorem because we are treating with infinite dimensional symmetries. In the Coleman-Mandula theorem, they use finite dimension. So this changes the hypothesis of the theorem. So it's the same spirit, but it's not exactly the same. You see? So it's nothing wrong with the principle.
Okay.
You see?
Yes. Thank you.
Okay, so I was saying that we can kill the logarithmic branches by killing the coefficients that goes along the Legendre functions of the second kind. These are functions that I will. When you solve the equations in hyperbolic description for the fields, you will obtain the Legendre equation, which is usually that the one appears in the physics. But by using the parity conditions, we'll kill one of the branches. One of the branches is the one that with the 1 over r decay is the Legendre polynomials branches. And then we have these logs that are coming from the Q branch, which are associated to the functions of the second kind. And also, if you solve the equations close to future null infinity and then close to past null infinity, you can verify explicitly that if the logs are absent, the qualities what that one obtains in the antipodal matching conditions, which is really nice. So because we are killing these logs, antipodal matching conditions are emerging. Okay. So now we'll I will explain in the time that remains. I will explain how to relax a bit more the asymptotic conditions. So we have in the literature proposals to generalize the asymptotic behavior of the gauge potential. And these new symmetries, which are overleading symmetries, because they are associated to a part of the generator which is growing linearly in the radial coordinate at infinity. These were symmetries proposed by Campilli and Lada in, I think, 2016. And very interestingly, they found that these new symmetries are related with subleading subtheorems. So we wanted to study this problem in spatial infinity, and we'll see what we can find. But we will start with something that is a smoother than a radial behavior. That is a log. Let's see what's happening with the log. And for example, we can relax in the same spirit, doing the same as Henneaux and Troessaert. We can relax by a log, for instance. And we obtained we were really surprised because the presence of these logs really solves this ambiguity problem of the angular momentum. That was not a problem, but it was a feature of the theory. But we can solve or find, we can find a definition for Lorentz charges, which are gauge-invariant. I will show you how is this working. As I told you, I think this behavior does not lead to any divergence in the symplectic structure, and we have to ask just for the same condition as before, which is the R-4 behavior of the Gauss law. So the Lorentz boost problem can be solved in exactly the same way. So we will deform the symplectic form by a boundary chart in the canonical variables of the extended Hamiltonian formalism. So if we take the variation of the symplectic form with respect to the boost, we'll find an extra term, which is this one, which is associated to the log branch. So for solving the problem, we will use almost the same boundary term for the symplectic form, which is related to a log behavior now in the time component of the gauge potential. By doing this, we will find, I will not show you the exact transformations. You can find in the paper that I will show you. This is the exact paper, the archive number. But you can find that by doing that, the new symplectic form is finite and invariant under Poincaré transformations. So now we have the canonical symmetries. All the symmetries are canonical in this case again, and we obtain this algebra. We obtain Poincaré, okay, the Poincaré killing vectors, and also we obtain a relaxation of the parameters by log terms. So we will find, using parity conditions on all the game, we have to play all the game again, and we'll find that the even parts of epsilon bar and mu log, which is a log relaxation of the mu parameter associated to the transformation law of the time component of the gauge potential, and the odd part of the remaining functions, we'll find that they are improper gauge symmetries, which is very, very nice. Okay, so we have these two gauge, two kinds of charges. But now if we compute the Poisson brackets, doing the standard computation, this is by taking the charge of 1 and then the charge of 2 associated to the second parameter, and this must be equal to the second variation of the variation of the first charge. We obtain this algebra. Okay, we obtain Poincaré, we obtain the cross term that Marcelo was pointing out, and also we obtain this term here, which is a central charge between the U1 charges and the new log U1 charges. These are the central charges, you see. And yes. So, okay, we said we have central charges, but we realized something, that the presence of these central charges will allow to decouple, indeed, all the U1 charges from the Poincaré algebra. This is equivalent to change this semi-direct product by a direct product here, which has strong implications. So the mechanism to see this is that we can write the Poincaré algebra in this prescription. This is the Lorentz algebra, okay? this is the commutator between Lorentz, the Poisson bracket between Lorentz algebra, the Lorentz generators and translations. Then we have that Lorentz with respect to the U1 charges and Lorentz with respect to the log U1 charges are different from 0. And also we have the central charge between the usual U1 transformation and the log U1 transformations. This is a central charge. So the question is, would it be possible to find a redefinition of the charges in such a way that these two are 0? Because in that case, we decouple the U1s from Lorentz. And the answer is yes. This is the redefinition. So we have to shift the Lorentz generator by a quadratic combination of the U1 charges. If we do that, we can find that this is a nonlinear automorphism of the Lorentz algebra. And this is working because of the central charge, really. So this mechanism is implemented in the phase space with charges and everything by doing suitable field-dependent gauge transformations. We can show that these transformations are not affecting anything, and we will publish a paper soon about that, about these field-dependent gauge transformations, and we'll show how we can use the mechanism really in higher dimensions and also in supergravity and yes, and supersymmetric theories. So this is a paper where you can find all this detail, transformation laws and everything, all the technicalities associated to the computation. So final remarks. I think that I'm okay with time. Something that it should happen, but I haven't computed, but it would be interesting to compute, so I'm leaving the problem on the table, is that these parameters, epsilon log and mu log, should combine in one function of the sphere at null infinity. So we have to, in some way, relax the boundary conditions at null infinity. I'm trying to see where are the logs there. This is something that is not done. This is a question of Eloy. One thing that, okay, where this is going to stop, because we can put logs, we can put order R, but what we found that this seems to stop at order R indeed. Order R square, we're not able to find boundary conditions or parity conditions or any restriction, any condition that is consistent with Poincaré in such a way that we kill the divergences in the symplectic form and in the charges. And this is in agreement with Campilli and Lada by using completely different statements in the context of null infinity. They also stop R at order R. So one thing that is interesting is that order R, the order R behavior, the order R behavior of the gauge parameter, because we relax the gauge parameter by a linear function in the radius, will render the 1/R gauge transformations improper. This is something that is very curious. And we found that these are conjugate each other. The overleading and the subleading, they are conjugate each other and they have a central charge which is different from 0. So again, the theory is protecting itself, and we can find invariant gauge-invariant Poincaré generators, even in this case. This also in the paper that I show you, the one that we published with Mark at the beginning of this year. Higher dimensions, one could ask. This is something that we deal with. We are already deal with. First, in this paper by Mark and Cedric. And then I found that it's possible to relax a bit more the boundary conditions in such a way to put to add to the set of solutions to the generalization of the magnetic monopoles in higher dimensions. It should be a brane or something. Okay. So to be done in this case, well, the match with null infinity, and for that we had to study what is the problem at null infinity. Maybe this could shed light about new sublimits of photon theorems, or maybe memory effects associated to these log terms. It's something that we don't know, but it's interesting, I think, to address in the future. So the next question is, what about gravity? And this is something that we will see next tomorrow. Okay, thank you.